Monday at 5 o'clock. Can I just remind you that you will need your gold book and a calculator. So please bring those along to the class table. We'll put a note up on Blackboard about that. So that's the class test. Any questions about the class test itself? All happy? It's going to be 45 minutes, so please make sure you get there on time.
Is the lecture today included in that class test?
No. So the material in today's lecture is not covered in the class test. Okay? Everything before that, everything you've done so far is. So whatever that is, section 0, section 1, section 2 of the course. Any other questions? All happy? Okay, the next couple of lectures cover something called runoff triangles, and this is really a little bit different to probably everything else in the course. So we could have slotted this in literally anywhere. Okay, this could have formed the first 2 lectures. We could have had it right at the end of the course, in the sense that it doesn't really rely on any of the other material. So in the next 2 lectures, you will not see any mathematics apart from a bit of adding up and a bit of multiplication and a bit of subtraction. So there are no statistical models being introduced in these couple of lectures. So you can forget about the Pareto distribution, at least for the next 2 lectures. Okay? This is very simple stuff in terms of the actual tools that you're going to use. The only kind of difficult bit is really getting your head around the idea of what to do. We'll come to that as we go through. So what we'll do today is basically look at a very simple method called the chain ladder method. And it's all to do with trying to estimate money that the insurance companies need for future claims. So they might know about claims, but they haven't yet paid off the money, and it might be a while before they can do that. So it's a very simple method for predicting, estimating monies needed for future claims. So we'll look at the basic idea of the method, and we'll finish up today just by looking at a simple idea for trying to judge whether the method is actually any good. In the second lecture in this part, which will be on Tuesday, we'll look at tweaking the basic method to take into account, for example, inflation. So this is the main point. In a lot of areas in insurance, the insurance companies don't pay the claims immediately the event happens. So in motor insurance, for example, okay, the insurance company pretty much knows immediately that an event, an accident has happened, but it might take a while before things are resolved and they know how much the claim is, and then they pay the claim. So that's the kind of issue. Some other examples, the first one I've just talked about in terms of car insurance. But the same kind of idea applies to any other area of insurance, pretty much. So subsidence claims on buildings insurance. So it might actually be quite a while after the subsidence has occurred before any claim is paid off. You employ some kind of assessor to work out whether the insurance company is liable, and if so, then how much money should be paid. Health malpractice cases, quite often in these cases, the insurance company may not even know that the event itself has happened for quite a period of time. So there's this kind of delay between an event happening and before a claim is fully paid. But of course, what an insurance company does need to know is how much money to set aside for these claims in each year, in the future, that result from these kind of events that happen in different years. There are a couple of kinds of, sometimes you distinguish between different types of situations. So some events or accidents the insurance company will actually know about. They may have started to pay something towards a claim, so they may have made some kind of interim claim payment of, let's say, £5,000, and then they'll settle up maybe a few months in the future, or maybe it's the following year when the claim is fully resolved. Those are referred to as case reserves, the money you need to set aside for those kind of claims. Future claims for events that have already happened, so these are incurred, events that have happened but have not yet been reported to the insurance company, so the insurance company doesn't know they've actually happened, although they have. Those are sometimes called these incurred but not reported reserves. Okay, so there's this simple idea which is referred to as run-off triangles as a kind of method of using historical information to predict the amount of claims or the amount of money that is necessary to pay off claims. As I say, the method itself is very simple, but you have to realise that in practice, of course, there are experts, actuaries within the field who might use this tool for simplicity, but tweak things left, right and centre using their knowledge about certain situations. Okay, so it's not as simple as it kind of seems. It's not just a mathematical exercise. All right. Well, here's the basic idea with some numbers. Hopefully, all will become clear. So I think the key thing is to really understand the structure of this kind of table. So here we have a number of rows for this table. So each row of a table corresponds to a year in which accidents happen. For example, if this relates to car insurance, then it would be the number of car. Each row would refer to car accidents happening in a particular year. The numbers in the table, as it says at the top, are actually cumulative totals of claim payments actually made by the insurance company in different years. So the columns of the table relate to the delay between when the accident happened and when the payment was made. So for example, if you take the top row of the table, so the top row of the table corresponds to events that happened back in 2008. The first column with the 0, this is called development year 0. This basically reflects payments made pretty much immediately after the event. So you have a total there of £786,000 that the company has paid in 2008, corresponding to events, accidents that happened in 2008. The number in the next column, again on the top row, refers to, again, the cumulative claim payments made, okay, by the end of the following year, so by the end of 2009. Again, still referring to accidents that happened in 2008. All right, so some claims immediately paid off. Then you have some more claims that are paid off in 2009. So by the end of 2009, about £1.4 million in claims has been paid. Okay, in the next column, development year 2 would correspond to the year 2010. Claims are paid 2 years later, 2 years after 2008, and by the end of 2010, about £2.2 million has been paid of claims, and so on. Okay, and then the final column in this table, development year 4, is 4 years after the accident year, so this would correspond to 2012. So by the end of 2012, the company has paid off £2.5 million worth in claims, corresponding to the accidents that happened back in 2008. And the assumption here is, for the setup of this table, the way we've done this here, is that all of the claims are paid within 4 years. Okay, so again, that is down to judgment of actuaries. That can be flexible for some types of insurance. Maybe you need to extend the number of years in this assumption to 5. Maybe you could limit it to 2 or maybe 3. And then you look down the other rows of the table. So the second row corresponds to accidents that happened in 2009. So the 904 there refers to payments made almost immediately, i.e. in 2009. 1575 would refer to the cumulative amount of claims paid by the end of 2010. Okay, so that is 1 year later than 2009. Okay, similarly across the row, and 2796 would refer to the cumulative total of claims paid by the end of 3 years later, which would be by the end of 2012. Now I'm assuming here that we're all sitting at the end of 2012. So this cell up here is the future. All right, so this little cell up here refers to 2013. So we don't know what we need to pay out in 2013 for claims or for accidents that arose in 2009. Okay. Next row down, accidents happened in 2010. We pay off some stuff immediately, some further claims in 2011, claims in 2012. So in that row, we have these 2 cells that refer to 2013 in the future and 2014 that we don't know about. We don't know what claims are going to come in. And so on. So the final year for this table that we know about, assuming I'm sitting at the end of 2012, we've got some accidents that have happened in 2012. Some of the claims have been paid off immediately, all right, but a lot of claims have yet to be paid, and they will be paid out over 2013, 2014, up to 2016. Again, the assumption is everything will be paid off within 4 years. Okay? So the top triangle, the top half of this grid, is historical information, refers to claim payments we've paid. All right, the bottom half, the empty triangle, the red cells, that is in the future, and you want to estimate claim payments for those cells. And what we're going to do essentially is use the historical data to make some predictions for those cells. That's the basic game. Okay, so if you can understand the structure of that table, I think things will be pretty simple for the next couple of lectures. Okay, I think I've covered all the points on this slide in my ramble. Accident year. Often this is referred to as the origin year, so you will look in textbooks and it will say origin year. Accident year because historically this kind of method was used initially for car insurance, okay, but it can be used for other types of insurance. Okay. Claims, again, assumption is that claims are fully paid off after 4 years in this particular example, but as I say, 4 years chosen on experience, and it may vary from insurance types, across some different insurance types. Okay, so the chain letter method, which we'll have a quick run through. Just to point out this last bullet point, 2008 is the first year for which we have full information. So if you go back to this table here, we have full information for accidents that happened in 2008 and obviously before 2007 and so on. But we don't have the full information for 2009 and the following years. Okay, we have bits of information that we don't know about and we want to predict. Okay, so the basic idea is that we'll use the historical information to predict into the future, and essentially we're going to assume that payments emerge in a similar way in each year, and we're going to use this idea of kind of proportionate increases in these cumulative payments, and we'll end up calculating things called development ratios. So if I go back to this original table here of payments made, the idea is to use, in the most simple case, is to use the full information that we have for 2008 accidents and calculate the increase in these cumulative payments across the development years. So for example, going from development year 0 to 1, the proportionate increase, well, we just divide 1410 by 786 to get some kind of multiplicative factor that tells us how the cumulative claims have increased from development year 0 to development year 1. Okay, and that factor is something like 1.7. Similarly, we can calculate the increase from development year 2 to, year 1 to development year 2 by dividing 2216 by 1410. That tells us how the cumulative claims have increased between those 2 years. Obviously for accidents that happened in 2008. But the idea is that you'll use those factors, those ratios, and apply them to the following years in order to predict numbers for these red cells here. Okay. So, again, these are just some examples. So this one I've calculated here. The year 1 ratio, the year 1 development ratio, would just be taking 1410 divided by 786 to get a development ratio 1.7939. Okay, so that is just this number divided by this number. Okay, so you've got a 79% increase in the cumulative claims going from development year 0 to development year 1. Sometimes, again, they talk about grossing up factors rather than these development ratios. That is simply the inverse, basically the inverse of that number. Okay, so if you take 786 divided by 1410, think of that in percentage terms, that's about 55%. And what that's telling you is the proportion of the total claims made by the end of development year 1 that actually occurred in development year 0. Okay, but it's pretty much, it's the same thing as this thing. It's just the inverse of your development ratio. Okay, so in a similar way, we can calculate the other development ratios based on the year for which we have the full information, which is 2008. Okay, so I've just calculated those in this box down in the bottom left-hand corner. This is the original table that we had a few slides ago. These are the yearly development ratios going from development year 0 to 1, that's the 1.79. 2216 divided by 1410 is 1.57, and so on. Okay, so you calculate each of those development ratios, and it will be these factors now that we will apply to the information that we have for 2009, 10, 11 to get the numbers for the bottom, the empty triangle at the bottom. Okay, so for example, starting up here, if I want to estimate the total cumulative claims by the end of 2013 for accidents that happened in 2009, what I do is just take the 2796, okay, and I multiply it by the development factor that I've calculated based on 2008. Okay, that development factor was 2519 divided by 2440. All right, this development factor down here, this factor 1.0324. So you're just applying that factor to this 2796 to obtain my estimate for this cell here. Okay. Then move down a row. What I need to do first is estimate the number for this cell here for development year 3. Okay, so what I do is I take this number here, 2880, and I multiply it by the factor that I've calculated from here, which was 2440 divided by 2216. Is that right? 1.1011. Right, so 2880 multiplied by 1.1011, that will give me a prediction for this cell. And then I take that number and I multiply by the development factor for year 4 to get the prediction for that cell. So in other words, I take 2880 multiplied by 1.1011, then multiply by 1.0324 to get the predicted cumulative total for this cell here. And so on. Then you go down to the next row, and then down to the next row. So finally, you'll end up filling up all the cells in that lower triangle. The last number that you'd fill out would be this one here. That final cell would be the predicted cumulative total of claims by the end of 2016, and that's obtained by taking this number here, 1182, multiplying by this year 1 development factor times this one, times this one, times this one. That will give you the cumulative total in that final cell. Okay. That summarizes that whole process. So those red numbers are all predicted cumulative totals. So what you might want to do is just in your own time, just check that you can get each of those red numbers, just so that you know how this process is working. Here's one particular example referring to year 4 of accident year 2009. That's the first one we started off with. So 2887 is obtained by multiplying 2796 by that year 1 development factor 1.0324. Sorry, the year 4 development factor 1.0324. Yeah.
How do we know how good the predictions are?
How do you know how good the predictions are?
Yeah.
Well, you don't until the end of 2016, when you have the actual claims data in. Okay. In a minute, we'll just look at a kind of very rough and ready idea for maybe assessing how good it might be. But you're not going to know exactly how good those estimates are, obviously, until you get your claims data in, because it's in the future. All right, so just going back to the initial idea, what do we want these numbers for? You want the numbers so that you can set aside some money to cover the future claims. So what is that reserve that you need to set aside? Well, just to point out at this stage, it is not the sum of all of those red numbers. Okay, because don't forget that each of those red numbers is a cumulative claim at a certain time point. What you need is the sum of the red numbers in that final column. Okay, so the first, the 2887 is the total amount of claims that you would have paid off for accidents that happened in 2009. 3274, that's the total amount of claims that you will pay off for accidents of 2010, and so on. So the total amount of money that is required, or the total amount of claims, will just be the sum of those 4 red numbers in that final column. Okay, is that the reserve that you need to set aside? No, because you've already paid off some of those claims. Right, so for example, if you take the 3788, yes, that's the total amount of claims that you need to pay for accidents that happened in 2012. But don't forget, you've already paid off a part of that. You've already paid off 1182 in 2012. All right, so the reserve you need to set aside would be 2887 minus what you've already paid for accidents in that year, 2796, plus 3274 minus what you've already paid for those accidents, which is minus 2880, plus 3827 minus 2142, plus 3788 minus 1182. That little summation will give you the amount of reserves that you need to set aside for future claims. Okay. Now, that is really it. That's all you need to be able to understand. There are various tweaks on that very basic idea. The first tweak is just trying to take into account more of the historical information, because what some of you might have already realised, yes, what we've done here is to calculate these development factors just based on the full information from 2008, right? But we do have some information for accidents that happened in 2009. So we know for those accidents how claims developed or emerged, at least over 3 years. Right? Perhaps not to the 4th year, but we have some further information for accidents that happened in 2009 that we haven't so far used in trying to predict the future. Right? We haven't used that information in calculating the development factors. All we used was the information from the top row of the table. So the obvious thing to do now is to at least use the information that we do have from 2009, 2010 and 2011. So for example, if I calculate the year 1 development factor, all right, I'm not just going to use information from 2008. I'm not just going to calculate the factor as 1410 divided by 786. I'm going to use all of this information here across all 4 accident years, 2008 to 2011, and somehow combine all of this information to calculate a single development factor for that year. Similarly, if I'm calculating a development factor from year 2 to year 3, again, why not use the information from 2009? Because I have that information. I know how claims developed from year 2 to year 3 for accidents that happened in 2009, as well as in 2008. Right, so our first little tweak is just trying to calculate better development factors and not just use information from 2008. Okay, did I miss something here? Oh, yeah, okay. Well, on that point, you've actually got 2 slightly different methods of calculating development factors by combining the information. You can either simply take an average of the ratios. All right, so what I can do is, for example, for the year 1 development factor, I can calculate this ratio, 2008, 1410 divided by 786. I can calculate similar ratios for 2009, 2010, 2011, because I've got all the information, and then I can take the average of those 4 ratios. That would be one way of doing things. Typically, and this applies to kind of statistics in general, if you start taking averages of ratios, that average that you obtain can be a little bit unstable, particularly if, in this case, for a particular year, if total claims maybe are relatively small compared to other years, you calculate a ratio for that particular year where the totals can be quite low, your ratio can be a little bit flaky, right? It might be quite extreme, and if you take an average of 4 ratios that includes one extreme ratio, then you might get a kind of combined ratio that's too high. So rather than take average of ratios, what we do is take, in a sense, a ratio of averages, or a ratio of sums. So what we would do instead is basically, if I wanted to calculate the development ratio, the year 1 development ratio from here to here, I would sum the claims, the cumulative claims across these 4 years, so add up those 4 numbers, add up these 4 numbers, divide 1 by total, which is what is going on this slide here. All right, so I calculate my combined development ratio by pooling the information across all 4 years that I have the information for, and my combined development ratio for year 0 to year 1 would be the sum of the numbers in this column here divided by the sum of the numbers in this column here, and my ratio would be 1.7775, right, which is slightly different to the ratio that you calculated based just on the 2008 data here. Okay. Then you can repeat, obviously use the same idea for calculating the year 1 to year 2 development factor. All right, so what you do there, pull the information, add these numbers in this column here, divide by the sum of the numbers in this column here to calculate my combined year 1 to year 2 development year ratio. Repeat for development year ratio 2 to 3. All right, so we've now just got 2 years of information to pull. My year 2 to year 3 ratio is 1.10. And then finally, well, can't do much with the year 3 to year 4 ratio. I've only got information from 2008. So this ratio is in fact exactly the ratio that we used initially. So you get, again, you're just getting a set of development ratios which is using more of the information. These development ratios typically will be different to those just based on 2008. Right, but again, same method now applies. You're using those development ratios to predict into the future in exactly the same way as we did before. Okay, so I haven't filled in all the numbers in this table at this stage, but just to show you again an example of how it works. So you have your 4 development factors. Oops. So if I just go back here, the year 0 to 1 ratio was 1.775. So I'm going to apply that down to this number here, 1182. If I multiply by my combined development rate, year 0 to 1 ratio, I will get my prediction for this cell. Okay, and that gives me 2101. Right, 1182 times 1.775. Once you've got that number, then I can multiply by the combined year 1 to 2 development ratio to get my prediction for this cell here, So 3332 is 1182 multiplied by the year 0 to 1 ratio, multiplied by the year 1 to 2 ratio, and so on and so on. And I can equally fill up all the cells in the bottom triangle there. And do we do that on the next slide? Yes, we do. Okay, so again, filling the future in a sense. And those red numbers will be slightly different to the set that we obtained initially, but perhaps that is going to be a better set of numbers to use because it's based on more of the historical information. Again, just to recap about the total reserve, it's not the sum of all of those red numbers, it is the sum of the red numbers in the final column minus what you've already paid off. So it will be minus 2796 minus 2880 minus 2142 minus 1182, which is basically equivalent to this little formula down here. All right, so my predicted reserves that I need to pay off future claims corresponding to the accidents that happened in these years is 4866. Now, obviously, kind of going forward, there will be claims, there will be accidents that will happen in 2013, 2014, and so we're not accounting for those accidents in this reserve here. This reserve here corresponds to claim payments that we'll have to make in the future by the end of 2016 for the accidents that happened up until the end of 2012. Okay. All right, last 5 minutes. Just a few points on the kind of assumptions that we're making here in using this method. And then the idea, which the gentleman at the back was asking about, how do you know how good this is going to be? So we'll have a look at least what we might do initially to have a stab at that. So the first basic assumption that you're making here is that the development ratios that you're calculating, they apply to the accidents that happen in each year. Right? Now there's no reason to suppose that's necessarily the case, but that is an assumption that you're making when you calculate these development factors. You're applying them to accidents happening in different years, and the assumption is that the claims for accidents that happen in a particular year will evolve over the development years in exactly the same way. Okay? Now, if again, professional judgment can sometimes be used to kind of tweak things if you realise that perhaps for a particular year something a little bit odd is going on in terms of the claims and the developments. Again, throughout this really professional judgment is used in addition to this very simple idea. The other thing to say is, of course, what we haven't used anywhere at this stage is information about the number of claims. Okay? We'll mention that in the next lecture on Tuesday, but all we're using here is information about the total amount of claims that's happened, not the number. And the other big thing that we've kind of conveniently forgotten about, and some of you may have noticed this, is of course that we've not done anything about inflation. Now it might be that the numbers that we've seen in the table that refer to cumulative totals of claim payments, they may have already been adjusted in some way for inflation, in which case it's kind of okay. But again, what we need to do really is to tweak this whole idea to take account of inflation if those figures have not been adjusted. So, in other words, going into the future, we've estimated claim payments for 3 years' time, but of course we don't know what inflation might be in 3 years' time. We need to at least build that into our method, because it's likely, for example, that 4866 is not going to be enough money to cover claims into the future because of the inflation effect. Okay, so that's one thing that we haven't covered yet. We will do in the next lecture. Okay, final thing to say is something a little bit about model checking. This is a very rough and ready idea to get a feel for how good this chain ladder method might actually work. So again, very simple idea. You can use the development factors that you've calculated, right? We've calculated those things and we've used them to predict the future. But you could say, well, why don't I use those development factors and actually predict what my claim payments would be and compare them to what has actually happened for historical information. Again, I've probably explained that extremely badly, but if we go back to our original table, this is the first table we saw, these were the actual claim payments that we've made so far. All right? So I'm just highlighting these are actual payments. So what I'm saying is, what we could do is we could try to predict these numbers over here. I know what I've actually paid in development year 1, but what I could do is predict what I might pay by taking this number here and multiplying this number by my development factor to get a prediction for this cell here. Okay, this is just going to give me an idea of whether my method is going to work or not. All right, so that's the idea. I'm going to make predictions for each of these numbers in this column, this column, this column, and this column, and compare the predicted numbers with the actuals. All right, so the next slide will show a set of predicted cumulative claim payments. Again, remember, all these numbers refer to cumulative claim payments. So this number here, where's my example? What have I done? 2008, development year 3. So I'm actually predicting 2452 as my cumulative claims payment for development year 3. And what I've done to obtain that number is take my original amount of claims that I've paid almost immediately, 786 down here, and then I've multiplied through by the set of development factors. The year 0 to 1 development factor, if you flick back a few slides, was 1.775. The year, where have I gone? Year 1 to 2 development factor is something or other, 1.586. Anyway, you multiply by the set of 3 development factors to get to a prediction for this particular cell here, 2452. All right, this number here, 2169, will just be 1220 multiplied by my year 0 to 1 development factor, which was 1.775. All right, so those would be what my, I really like to say model, I'll use model in quotes. This is what my model would predict, all right, for this particular development year here, corresponding to accidents in 2011. But I know what I've already actually paid out, 2142. So you could think about looking at the difference between 2169 and 2142 as a kind of error. All right, and you can work out those errors for each of the cells in your table, okay, just by looking at the differences between the predicteds and the actuals, and you'll get this set of green numbers. And so the idea is that this will give you a feel for how good your procedure might be. So, you might look at this set of numbers. Some will be negative, some will be positive, because you're overestimating and underestimating what happened. All of these numbers are relatively small compared to the actual levels of payments. Okay, so we were talking about payments of the order of $1 million or $1.5 million, or up to about 3 million. So these errors, if you like, are relatively small, a few £1,000s. So arguably, you could say maybe that you have some kind of faith in this method, although you don't know what's going to happen exactly in the future. So I'm not saying this is a fantastic idea that's going to allow you to predict perfectly or assess whether your method will predict perfectly, but it might give you an idea of how useful it will be. Okay. Chi-squared test. I mean, some of you might kind of be thinking, well, surely this is just a chi-squared test because I've got some observed numbers back here in cells, and I've got some kind of predicted or expected numbers. Chi-squared test generally refers to situations where you have numbers or counts, which you don't really have here. These are not counts. These are actual totals of amounts. So strictly a chi-squared test would not be appropriate to use in this particular situation. Okay, well, we'll finish there. A couple of references to some books. I particularly like the chapter in the Boland book. That's quite a nice read. On Tuesday, as I say, we'll be looking at slight adjustments to account for things like inflation. But I think once you've got the idea of this method, it's easy. There's no hard statistics. Okay.